Okay, now we're going to talk about something called even and odd functions, and you'll see this is very closely related to what we've already been talking about. So, even and odd is actually are algebraic conditions, but it turns out they're equivalent to some geometric conditions that we've already studied. So we say a function f is even if and only if f of negative x is the same as f of x. And so what we're saying is change the sign on x and the function stays the same. We've already looked at this before. We know that changing the sign on x means that it's going to be reflected over the y-axis, and now we're saying we reflect over the y-axis and the function stays the same. So it turns out that even functions are exactly the same thing as the functions that are symmetric with respect to the y-axis. So if it's an even function, it must be a function and symmetric with respect to the y-axis. If it's symmetric to the y-axis and a function, then it must be an even function. Of course, there are some relations that are symmetric with respect to the y-axis that are not functions, like the unit circle that we looked at earlier. So even degree power functions, y equals absolute value of x, polynomials with all even degree terms, for example, are even functions. So, for example, notice that f of x equals x squared is one of the examples we've looked at several times. It's an even function because f of minus x is minus x squared. And when you square a negative x or positive x, you still get the same thing. You get x squared, which was our original f of x. So notice what we did to check that, to see that it was even. We put in a negative x in place of x, simplified the formula, and if that turns out to be the same as the original, then it is an even function and it has y-axis symmetry. And it gets its name because even degree power functions are even functions. It's sort of a generalization of that. And remember, when we had even degree power functions, we had y-axis symmetry. Okay? Or even when we had power functions with even numerator over an odd denominator for the power, those also had y-axis symmetry. So those would be even functions. But there are other things that are even functions. Some graphs, some things that that show up here are certainly y equals x squared. If all the terms are even degree in a polynomial, that'll be an even degree function. Y equals absolute value of x is even. Anything that has y-axis symmetry will also have this condition. Now we say a function is odd, or an odd function, if and only if f of the opposite of x is opposite of f of x. And so what are we saying here is y is the opposite of x. That's the opposite of f of x. Let me see if I can that's not what I wanted to bring up. So we've got f of the opposite of x is the opposite of f of x. Okay, so when we put in this part right here, we're changing the sign on x, so we're reflecting over the y-axis. If we'll now put an opposite here on this one, then we'll be back to where we started. So we're saying we're basically, this is switching the sign on y, and this first one's switching the sign on x. So ultimately we're saying we're switching both signs, and that ultimately turns out to be just the original function. Well, if that's the case, then what we have is symmetry with respect to the origin. So it turns out that that's exactly what we have. An example of that, of course, no surprise to you probably, even power functions are even functions, and odd power functions are odd functions. So if we have f of the opposite of x, we take the, and f of x is x cubed, that would be the opposite of x cubed. Three negatives multiply together to give you a negative. So it's the opposite of x cubed. Well, x cubed is the original f of x, so it's the opposite of f of x. So you can actually test for even and odd at the same time. All you have to really do is put in, if it's a function of course, put in negative x in place of x in the formula. If that formula reduces or simplifies to the original f of x, then you've got an even function. If not, factor out a negative 1, and if what's left in the parentheses after factoring out a negative 1 is the original f of x, then it's odd. Now, it's very likely that it's neither one, because both of these things are very special algebraic conditions, and they're also very special geometric conditions as well. If I just scribble out some graph, whether even if it's a function, it's likely to not have any kind of symmetry at all, much less specifically y-axis symmetry, even function, or origin symmetry, which would be odd functions. Okay? A function can't be both even and odd, with one exception. If it's just y equals 0, that's both even and odd. It has both origin symmetry and y-axis symmetry. But otherwise, it can't be both even and odd. A relation can have both y-axis and origin symmetry, but then it's also going to have x-axis symmetry, and it's not going to be a function unless it's just on the x-axis only. So a function, with this one exception, cannot be both even and odd, but it can certainly be neither even nor odd. Also remember one thing, that a constant function is actually even. So, it's a 0 degree, that's 0 is an even number. So, for example, let's look at a few examples. F of x equals 3x to the fourth plus 2x squared minus 3. Let's see if it's even or odd. Put in negative x in place of x, do f of negative x. Notice that we have even powers in both cases, so those negatives basically cancel out. And look at that, we're right back where we started at f of x. So that's an even function, but it's not odd. So it's an even function. The next one has all odd powers, 1, 3, and 5. So when I plug in negative x there for g in part B, we get negative x to the fifth is the opposite of x to the fifth. The negative x to the third is the opposite of x cubed. And of course the opposite of x is the opposite of x. And pull those negatives out front, and we get negative 3x to the fifth minus 2x cubed plus 3x squared. And we notice that's not the same as the original, so it's not even. So then we see if it's odd by factoring out a negative 1. What's left in the parentheses, and once you factor out a negative 1, changes all the signs. And so that's 3x to the fifth plus 2x cubed minus 3x, which is our original g of x on the inside. So what you ended up with was a negative 1 times the original g of x. That's exactly what makes it odd. So the graph of the function up there in the first one, 3x to the fourth plus 2x squared minus 3, whatever that graph looks like, it's going to have y-axis symmetry. Let's check it out here. Okay, y equals 3x to the fourth plus 2x squared minus 3. And notice those are all even degree terms. There's powers of 4, 2, and 0 basically. And so, okay, there we go. There's the graph. And notice we see the y-axis symmetry. If I were to add another term to this, minus 0.5x to the sixth, for example. Hard to, oops. Sixth. Now we get a graph that still has y-axis symmetry, right? Now let's look at the other one with it's the 3x to the fifth, 2x cubed, minus 3x. 3x to the fifth. Y equals 3x to the fifth plus 2x cubed minus 3x. Now we haven't studied what this graph's going to look like, but we do know it's going to have origin symmetry. So whatever we see, say on the right half of the graph, we can rotate it around to get what's on the left half of the graph. Okay? And if I add an odd term to that, everything's going to work out fine. So if I add, say 2x to the, say 7th, we're still going to get, that looks a lot the same. There we go, minus 2x to the 7th. Now it looks a little different. But we see that that is still got that origin symmetry. If we were to rotate the whole thing 180 degrees around, the graph looks the same. Okay? Alright, however, notice if I add, what if I add this? What if I add 5? Will that still be? Well, no. That's going to shift it up 5. We could have figured out that was what was going to happen. And now it no longer has either y-axis symmetry or origin symmetry. Actually, it still has some symmetry. It's symmetry about this point at 0, 5. But it's not one of our special symmetries of y-axis or origin symmetry. So this is neither even nor odd. Something kind of like that happens in this last one here. It's got both even degree terms and odd. It's got 5 and 3 on the powers of x. Those are odd degree terms, but a constant is in power 0 basically, so that's an even degree term. So pull in negative x. That's negative 5x to the 5th minus 7x cubed minus 3. That's not the same as g of x. When we factor out a negative 1, what's left in the parentheses is not the same as g of x either, because the sign on the last term is different. So it's neither even nor odd. If we were to graph that one, it won't have y-axis symmetry or origin symmetry. Might have some other symmetry, but not those two particular ones. We'll do the summary in another video.